Welcome back to our journey here. Today we're going to use quantum mechanics to identify electron configurations. Okay, we have introduced our various orbitals in our atom. They have different energy levels, they have different shapes. There are some rules, however, to what orbitals are possible. When you're on the first floor of the apartment building, that first shell, we only have s orbitals available. As you move up to the next floor, you're able to have s orbitals and p orbitals. By the time you get to the third floor, now you also have the option of d orbitals, but the only time you'll see f orbitals is when you get to the fourth floor or above. Our apartment building here is built like an upside down pyramid. There are more options as you get to that higher energy level. All right, we've gotten to a good point. We can describe all of the various orbitals that exist in our atoms. Now we want to get into this idea of, electron configurations. Which of those orbitals actually has electrons in them? And how many electrons are in each of those orbitals? We can do this with our electron configuration or with a box diagram, an orbital diagram. The electron configuration is a list of orbitals where you use a superscript to show how many electrons are in that orbital. The 1s orbital, s means that it is spherical shape. 1s means that we have the first floor version of that, the smallest, lowest energy version of that s orbital. The superscript 1 means that we have a single electron living in that orbital. This is a nice, straightforward list of electrons and orbitals. If you want more detail, we could try to draw these pictures, but drawing the pictures of the orbitals every single time is going to become, real annoying real fast. So instead, we can draw a box diagram, an orbital diagram, where instead of drawing the spherical or peanut or double peanut shapes, we're going to draw every single orbital as just a square or rectangle box. Drawing the s orbitals isn't too hard, but what if we're talking about a p orbital? Well, now we're trying to draw peanut shapes and it's going to be a whole mess of drawings. Instead, we can just draw our 2p orbitals as a series of boxes. 3 peanut shapes turns into 3 boxes. To show how many electrons are in those boxes, how many electrons are in those orbitals, we can draw arrows into our boxes. One property of our electrons that we haven't actually talked about yet is spin. Electrons can have either spin up or they can have spin down. So actually we have 2 different flavors of electron. We like to draw spin up electrons as up arrows, spin down electrons as down arrows. We want to do an example up at the top. If you have 2p6, that means we have 6 electrons in those 2p orbitals. We can do our little picture here, but this is going to be hard to draw and understand at a glance. So instead, we can draw our box diagram. 3 boxes representing those 3 peanut shapes. And then we want 6 arrows inside of those boxes to show that we have 6 electrons in those orbitals. You can draw these arrows with the double-sided head or the single-sided head. It's fast to draw it just with half a pointed arrow, but you do you. Now that we know how to write our orbitals and show how many electrons are in each of them, we need a set of rules to decide where to put the electrons in our atom. There are 3 rules to dictate this. This is the Aufbau rule, fill from low energy orbitals to high energy orbitals. The Pauli exclusion principle, which one way to say this is at most 2 electrons can fit into a single orbital, one pointed up, one pointed down. And lastly, Hund's rules, when we get to a set of equivalent orbitals, our electrons will spread out first and have identical spins before they start to pair up. That's our quick overview. I'd like to just jump into some examples, and we can circle back to each of these rules as they come up. Our simplest case is hydrogen, which has just 1 electron. When we're putting our electrons into our orbitals, we want to start at the lowest floor of the apartment building. That is going to be our 1s orbital. We have just 1 electron, and so we can put it in there. We can say we have 1s1 as our electron configuration. For our box diagram, we can say, oh, here is our box representing that 1s orbital. Since we have 1 electron, let's draw 1 arrow inside of it. Moving on to our second most simple atom, helium has 2 electrons. When we have 2 electrons, well, we can fit 2 electrons in each orbital. We can put both of those electrons into that 1s spherical orbital. In our box diagram, that's going to look like 2 arrows, one pointed up, one pointed down, in that 1s box. Once we get up to lithium, now we have 3 electrons. We can start by, again, doing that 1s orbital. Unfortunately, only 2 electrons can fit into that 1s orbital. We need to keep going until we've used up all of our electrons. And so we still have 1 left. We need to move up to the 2nd floor of our apartment building and go into the 2s orbital. Let's use that 1 electron. Let's put it into the 2s orbital. Here's what this picture starts to look like. 1s2, 2s1. Lots of numbers and letters here, but our picture is we have the 1s orbital, we have the 2s orbital, and our 3 electrons are hanging out in those orbitals. Instead of drawing the pictures of the orbitals every time, it's much easier to list out the electron configuration or to draw that box diagram. For beryllium, now we have 4 electrons. Start in the 1s orbitals. We can fit 2 of our electrons in there. Move up to the 2nd floor. We can fit our next 2 electrons into the 2s orbital. Our box diagram is going to look something like this. Our next element is boron with 5 electrons. Unfortunately, we can't put the 5th electron into that 2s because it's full. Only 2 electrons can fit in each orbital. So we need to move up to our next set of apartments. On the 2nd floor, we can have s orbitals and we can have p orbitals. When we're drawing the box diagram for our p orbitals, we need to remember they always come as a set of 3. So it's always going to have to be 3 boxes for those p orbitals. They never show up 1 at a time or 2 at a time. P orbitals are always a set of 3. Our 5th electron gets to go into at least one of those p orbitals. And so we have a picture like this, 1s2, 2s2, 2p1. Carbon with 6 electrons is going to exist as 1s2, 2s2, 2p2. The s orbitals are always a set of 1. The p orbitals are always a set of 3. If you want to think about the number of electrons, each orbital can fit 2 electrons. So our s orbital can fit a total of 2 electrons. The p orbitals are 3 orbitals, each of which can fit 2 electrons. We can fit up to 6 electrons into our set of p orbitals. We do need to follow that Hund's rule, which says let's spread out before pairing up. So our carbon is going to look like this in the box diagram. 1s2, 2s2, 2p2. Now that we've seen a few examples, let's revisit our rules. The Pauli exclusion principle says we can only have a maximum of 2 electrons per orbital, one of them spinning up, one of them spinning down. But since our orbitals come in sets of 1 or 3 or 5 or 7, we can have a total number of electrons in our sets of 2 or 6 or 10 or 14. Our Hund's rule that we just saw for carbon says that we want to spread our electrons out if we get to a set of orbitals. We can think about this like sharing an apartment or sharing a row of seats on a bus. If you're moving into an empty apartment building, great, we can grab our own apartment, we can live by ourselves. No roommates is going to be nice. If you move into an apartment and there's already someone living in one of the apartment rooms, you'd probably rather live by yourself than live with a roommate. There's a little bit of inherent tension that arises when you're living with someone. Or if you're grabbing a seat on the bus, if there's plenty of empty rows and there's someone sitting with an empty seat next to them, it would be a little bit odd, a little bit uncommon for you to sit next to a stranger if there are, infinite empty rows if you just walk an extra 1 foot. Electrons behave this way because they're negatively charged. 2 electrons living in the same place, those are 2 negative charges. They're going to repel each other. There's going to be some tension from 2 negatives, 2 of the same charge, being in the same spot. So if possible, our electrons will spread out. The second part of Hund's rule, we also want to have the same direction for our arrows, parallel spins. Our convention is let's just draw all up arrows first, spreading out. Then we can start to pair up with some down arrows once there's no other open orbital. The last rule we mentioned was this Aufbau Principle. We want to fill from the bottom up, fill in the bottom floors of our apartment before moving up to the higher floors. This is exactly what you would do if you were moving into an apartment with all your furniture and everything and there wasn't an elevator. If you have to carry things up the stairs, you're not going to carry them up more stairs than are necessary. Take the lowest one that's open. Same thing for our electrons. Let's go and find the lowest energy orbital to move into. Then if those ones are full, we can climb up another set of stairs. What's strange about our orbitals is that once we start to have more than 1 electron, the order of filling is not always exactly what you'd expect. Here is what the energy level for our orbitals actually looks like. It's not all of the things on the first floor, then all the things on the second, then the third, then the fourth, then the fifth. Actually, we have this strange pattern that we're going to just have to know. If you're filling from the bottom up, the first thing that we get to is the 1s. The second is 2s. Then we get to 2p. Then we get to 3s. Then we get to 3p. This is all what we'd kind of expect already. But there's an oddity here. After the 3p, we need to move to the 4s before we get to move up to the 3d. In fact, it's easier to get to that 4s orbital than it is to get to our 3d orbitals. This is predicted and explained by quantum mechanics. Unfortunately, we don't quite have the time to do all of that math. We're just going to have to trust that this is the right answer. To help us remember the order that we need to fill, well, we could just memorize the list. More fun is thinking about our upside down pyramid of our apartment building and picturing, oh, actually we get to climb up these diagonals when we're filling in our orbitals. We can start with that 1s, then we get to do our second diagonal to the 2s, then we get to do the 2p's and the 3s, then we get to do the 3p's, but before getting to the 3d, we're going to have to take this diagonal staircase up to the 4s. Then we can get to the 3d and the 4p. Same thing, we'll continue on this way. We'll get to the 5s before we move up to the 4ds, the 6s, oh, and then finally we get to have f orbitals after we get all the way up to the 6th floor in terms of our s orbitals. If we don't like this method of remembering the order, we can also use the periodic table. I'll show some examples of that in just a little bit. We've seen some examples. We've introduced our rules. That Aufbau principle, go from the bottom up. That Hund's rule, spread out before you have to pair up. And our Pauli exclusion principle, only 2 electrons fit at maximum in each orbital. Let's do a few more examples. If we're thinking about nitrogen, we have 7 electrons. We need to go in the order that Aufbau principle describes. 1s, then 2s, then 2p, then 3s, so on and so forth. We have all these orbitals available. They can be empty, they can be half filled, they can be completely filled, but we can at least list them all out and then start to fill our electrons into them. If you have s orbitals, you can fit at most 2 electrons in there. So 1s2 is the best we can do. 2s2. For our p orbitals, we can fit up to 6 into our set of p orbitals. But we only have 3 left. 1s2, 2s2, 2p3, that is all 7 of our electrons. I wrote out 3s, that orbital is empty, so we can just erase it and move on with our life. If you want to draw the box diagram instead, we have our 1s, our 2s, and our 2p's. The s orbital is just a single box. The p orbitals are 3 boxes. And now we need to draw our electrons. 1s2, 2s2, 2p3. Remember to follow Hund's rules. Let's have our electrons spread out before they have to pair up. Oxygen has 8 electrons. Same idea. 1s2, 2s2, 2p4. Here are those empty boxes. 1s2 is going to be 2 arrows. 2s2 is another 2 arrows. 2p4 is 4 arrows fitting into these 3 boxes. The first one, I like to choose the leftmost. The second one, oh, we need to spread out. The third one, I can still spread out. The fourth one, we can have a roommate if we have to. That's okay. There's no other choice besides pairing up. Here's the answer for fluorine. We'll leave that as an exercise for you to understand what all those numbers and symbols mean. We have two more examples here, neon and sodium. I'm going to leave those as practice, but we have one more hard one, which is bromine. Bromine has 35 electrons. This is going to be a lot. We can start by writing out our Aufbau order of orbitals. I'm going to stop the list here, but we could keep going. Once we have our orbitals, we can start to fill in our electrons. S orbitals are allowed to hold 2 electrons. P orbitals, we have 3 orbitals. We can fit a total of 6 electrons. Once we get back to our s orbital, we can only fit 2 electrons. Our p orbital here, that's a set of 3 orbitals, 6 electrons. S orbitals, that's 1 box. It can fit 2 arrows. The d orbitals, these come as a set of 5 orbitals. So we can fit a total of 10 electrons into them. Before we just fill in all the electrons willy-nilly, let's make sure that we are doing the right number of electrons. Right now we have 2 plus 2 plus 6 plus 2 plus 6 plus 2. So far we've drawn 20 electrons. We want to get 35. So, okay, let's keep going. Let's put all the next 10 electrons into those d orbitals. Now we've drawn 30 electrons in there. We want to get up to 35, and our p orbitals can hold up to 6. Holding 5 is totally fine. There's our configuration for bromine. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. 35 electrons in our bromine. This is where they are. We can describe exactly what orbitals have electrons, how many electrons are in each of those orbitals. It is time for a practice question. So let's grab some pencils, grab some paper, try to write a good answer for yourself. We can have a couple of wrinkles in our electron configurations. One common example is ions. When you add or remove electrons, you get to form charged atoms. In our electron configurations, simply add or remove electrons before filling in your electron configuration. For example, Na, sodium, should have 11 electrons, but if you have Na+, now it only has 10 electrons. Positive charges force us to give away electrons. Alternatively, if you have anions, negatively charged species, these have extra electrons. Neutral chlorine has 17 electrons, but with that minus charge, it has 1 extra. So now it has 18. Now that we've learned the basics for how to do our electron configurations, we can also introduce some shortcuts and pro tips. One of which is we can use the periodic table to help us. The periodic table is arranged according to the properties of our elements, which, as it turns out, correlates exactly to the number of electrons in our elements. The periodic table shortcut for figuring out the electron configuration utilizes this idea that we have different blocks or areas on the periodic table, which correspond to different orbitals. The two tall columns on the left correspond to our s orbitals, our s electrons. S orbitals come as one orbital. We can fit 2 electrons. Oh, check it out. Our periodic table is 2 columns wide in this area. On the right-hand side, we have what we call the p block of the periodic table. The p orbitals come as 3 orbitals. We can fit 6 electrons. Again, check it out. We have 6 columns for this area of the periodic table. In the middle, we have our d block on the periodic table. 5 orbitals in a set of d orbitals. We have 10 columns wide for that d block. This is not a coincidence. Our periodic table is arranged exactly based on our electron configurations. The period numbers on the left of the periodic table are like the floors of our apartment building. Those are the principal quantum shell. If you want to remember the order of your orbitals, just read the periodic table like a book from left to right, from top to bottom. First, we travel through period 1 of the s block, so we start with our 1s orbitals. Then we make it to period 2, and we have to travel through the s block and the p block. 2s, 2p. Then we make it to the 3rd floor. We get to travel through 3s and then 3p. Then we make it to the 4th floor. We get to travel through 4s. We get to make it to the d area, and then finally we get to make it to the 4p. A note here, we know that this is actually the 3 d orbitals. We just get to them after the 4s. So our numbering system has to be -1 once you get to that d area. For the f area of the periodic table, you need to subtract 2 compared to the period numbers on the far left. If this makes a little bit of sense, we can use our periodic table to kind of read the electron configuration for any given element. The number of boxes that you have to travel among a block corresponds to the electrons in that set of orbitals. So for example, if you're talking about neon, we have to travel through the 1s, and we have to travel through 2 boxes. We have to travel through the 2s, and we have to travel through 2 boxes. We have to travel through the 2p, and we travel through all 6 boxes, and then we get to our destination and we're done. Neon is 1s2, 2s2, 2p6. We can shortcut using our noble gases as well. If you want to abbreviate the first 10 electrons, we can write this as square brackets neon. This means, okay, start with that electron configuration for your noble gas, and then we can continue on after that. Unfortunately, we only get to do the square brackets for the noble gases, but using that noble gas shortcut does make our life a lot easier once we understand it. Here is our periodic table. We can do our example here as well. Let's look at bromine once again. Bromine has 35 electrons. So we can travel through the 1s, the 2s, the 2 P's, the 3s, the 3 P's, the 4s, asterisk here, subtract 1 for your D block. Traveling through the D's here, this is the 3 D's, all 10 boxes, and then 1, 2, 3, 4, 5 boxes to get to bromine. We're back to 4P5. We did this example earlier, kind of a longer way. We can also use the periodic table as kind of a nice shortcut. We can use our noble gas abbreviation as well. The first 18 electrons in our configuration are going to look exactly like argon. Here are those 18 electrons. Instead of listing out our first 18 electrons, we can just write bracket argon. This will abbreviate all this traveling that we did at the beginning. If we're starting with that abbreviation of argon, then we get to pick up just from here. Now we start with, after argon is period 4 on the S block, pass through 2 squares. This is the 3D area, pass through 10 squares. Now we get to the 4P area, pass through 5 squares. This is the same answer as this. We've just used a nice abbreviation to make our life a little bit easier. This is especially useful if we're talking about some of our heavy elements. One of my favorite, Ag, has 47 electrons. We can do the version we started with, that long version, or we can use the periodic table and try to get out to element and maybe start with whatever noble gas is closest and above that element that we care about. Once we identify that noble gas that is closest to our element but above it, we can start our electron configuration with that gas in square brackets. This bracket Kr represents 36 electrons out of the 47 that we want to care about. After Kr, we have to continue on. We get to the 5s area, travel through 2 boxes. Then we get to the D block. This is off by 1. Instead of 5, it is going to be the 4D. And we need to go 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 boxes. So we would expect 5s2, 4d9. There we go. That is our simple way of getting our electron configurations using our periodic table and this noble gas shortcut. The reason why this noble gas shortcut is nice, not only does it make things fast, but those first 36 electrons are actually held very closely to the nucleus, and they don't actually participate in our chemical reactions or in our bonding for the most part. So not only is it fast to write our electron configuration this way, but also we're not really losing too much vital information. Those first electrons really don't participate in much of our chemistries. All right, we've made it to the portion here where we get to try our own hand at these style of questions. You write the electron configuration for each of these elements. If you want to use that noble gas shortcut, you are welcome to. With that, we've accomplished our goal. Quantum mechanics allows us to identify electron configurations for any of our atoms that we might want to consider.
Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.